Now we come to lecture 2, which is electronic basics to prepare for the technician's license. So we start off with the most basic property of matter associated with electricity, which is electric charge. Bulk matter is neutral, which means that the number of positive charges in the matter exactly balances the number of negative charges. And so we do not see the effect of electric charge in everything. But if we do work on matter, so for example, this little girl's hair in the middle picture has rubbed against the plastic of the toy set she's playing on. What has happened is we have, by friction, separated charges in her hair. And because her hair is an insulator, the charge has remained separated. It can't flow along her hair to recombine again. And then that separated charge sets up an electric field, which interacts with charge on her other hairs. And the result is they repel each other to stand up, as in the picture. Now, this effect is certainly at least thousands of years old, but was first reported in writing by Thales of Miletus. And he observed it with amber, rubbing amber with fur to produce sparks and make the fur stand up and so on. The Greek word for amber is elektros. And so that is why the word electricity and electron have come down to us. The fundamental unit of charge in the international system of units, the SI systems, the metric system, is the Coulomb, and it's designated by the symbol Q. In terms of elemental charges, such as the charge on a single proton or the charge on an electron, 1 Coulomb is about 6.2 times 10 to the 18 fundamental charges. If this is the first time you've seen exponential notation, I hope you get used to it quickly, because we're going to deal with very large and very small numbers. And 10 to the 18 means that this 6 is followed by 18 positions of digits, or 6.242, and then 15 zeros after that. So separated charge gives rise, as we saw, to an electric field, and electric field are measured in volts per meter. When we do work to separate charges, like the friction that this little girl applied between the plastic playset and her hair, we do work in units of joules. So 1 joule is the work done by pushing against a force of 1 Newton for 1 meter. And we get work back when we allow the charges to recombine. The volt is defined as the difference in this potential energy between 2 points. And it is given by the electric field, which is measured in volts per meter, times the distance that separates these 2 points. So if we move 1 Coulomb together over a distance of 1 meter, we will get an energy from that activity of 1 joule, or we will require 1 joule of energy to separate 1 Coulomb of charge for a distance of 1 meter. So now let's look at electric current. A current of 1 ampere corresponds to 1 Coulomb of charge moving past a given point in 1 second. So let's look at a familiar example, which is the little AA batteries shown in this picture. The potential difference between the terminals of an AA battery is 1.5 volts. In electronics, you'll always be looking at potential differences, and therefore you'll always have to connect at 2 points. This may seem an obvious point, but very often people stick an oscilloscope probe on something without remembering to also connect the oscilloscope ground. So potential difference then between the terminals of the battery, 1.5 volts. The capacity of an AA battery is given as 2.5 amp hours typically. What that means is 2.5 coulombs per second, that's the amps, times an hour, which is 3,600 seconds, or about 9,000 coulombs of charge are separated in a AA battery. Thus, the available energy is this charge, 9,000 coulombs, times the potential difference to go from one terminal back to the other to recombine and then make neutral matter, which is a dead battery. So it's 9,000 coulombs times 1.5 volts, which is 13,500 joules. If we draw 1 amp from the battery, i.e. 1 coulomb per second, we will get an energy of this charge times the potential difference, or 1.5 joules per second. But a joule per second is a watt of power. So we get 1.5 watts of power. This argument shows by definition then that the power in an electrical circuit is given as the product of the current times the potential difference across which that current flows. Now, we've talked about insulators, the little girls' hairs where the charge remain stuck. Conductors, of course, like wires. But now we should talk about resistors. Resistors control the flow of current at a given voltage. So on the left, you see some pictures of resistors. Here is the circuit symbol for a resistor. And here's the color code that lets you work out what value of resistor you have. Resistors are things that decrease the current flow at a given voltage. So for example, if a voltage of 1 volt is applied across a resistor of 1 ohm, then a current of 1 amp will flow, the unit of resistance being the ohm in these metric SI units. Stated this way, this relationship between current, voltage, and resistance is called Ohm's law, most famously in the form V equals IR, or in other words, if a current of 1 amp flows through a resistor of 1 ohm, a potential difference of 1 volt will be generated across that resistor. If a current of 1 milliamp flows through a resistor of 1 kilo ohm, then 1 volt potential difference will also be generated. Other forms of Ohm's law are R equals V divided by I. So if a voltage of 1 volt applied across a resistor produces a current of 1 amp, then the resistance is 1 ohm, and I equals V over R. So in other words, if 1 volt is applied to a 1 ohm resistor, a current of 1 amp will flow. We measure potential differences with a digital multimeter. And so here's a picture of such a device with the 2 probes put into the 2 sockets for measuring voltage and the switch set on the voltage range. Once again, remember, you have to connect the 2 terminals, one to each end of the battery to make a measurement. There's a 3rd socket on here. That's for the case where you want to connect the leads in series with a circuit to measure the current through it, which you can also do by switching that switch to the amps range as shown there. Now, we deal with an enormous range of things in electronics, and you will hear prefixes used all the time. So let's start at the smallest, pico, 10 to the minus 12. One will most often encounter very small capacitors with values of picofarads. Nano, 10 to the minus 9. Nanofarads for capacitors again. Micro, 10 to the minus 6. Microvolts, maybe the signal at your antenna. Microamps. Microfarads, common for capacitors. Microhenries, common for inductors. Milli, 10 to the minus 3, millivolts, milliamps, millihenries. Things on the order of unity, volts, amps, ohms, 1 Henry inductors are certainly possible. Bytes in computers. There are such things as farad capacitors. Kilo, that's 1,000. Kilo ohms, kilovolts, certainly in old TVs, not too common these days in electronics. Kilobytes in a computer. Mega, so 10 to the power 6 or a million. Mega ohms, megabytes. And then giga for computer storage, gigabytes, terabytes, and even petabytes. And a giga ohm sometimes crops up in low noise circuits. Now, what makes a meter like this digital meter special is that it places almost no load. In other words, it draws essentially no current from the circuit. Let's be extreme and assume that the circuit was short-circuited through this meter. In other words, that had a very low resistance, so that it took a current of 9,000 amps or 9,000 coulombs in 1 second. Then that AA battery would be completely drained in 1 second, and the voltage would measure 0. So by having a device that takes very little current or charge from a voltage source, you can measure it accurately. We say that such a device has a high internal resistance. And we will come back to this idea when we talk about sources and loads in power transfer. But a meter is a thing with a high internal resistance. Now, the battery was a DC voltage source. We are interested in AC or alternating currents. This is because, of course, radio waves are generated by AC. We're familiar with the AC supply in our electric sockets. An AC waveform, of course, is any sort of current that changes with time. But for the purposes of this discussion, we'll confine ourselves to the simplest, which is a waveform that changes with time like a sine wave. So that would be the voltage equals the peak voltage times sine of 2 pi times the frequency times time. That's the mathematical expression. The 2 pi times time is so that as you go through every cycle of oscillation, the sine cycles back again to the start, as seen in this picture on the left. So here we start at 0, and here the value of the argument is 2 pi. The time this takes is 1 over the frequency of the waveform. The frequency of the AC waveform in the line sockets in your wall is typically 60 hertz, in other words, 60 cycles per second. The unit hertz is used in honor of Heinrich Hertz, the discoverer of radio waves. In radio, the frequencies can be millions of cycles per second or even billions of cycles per second. In an AC waveform, the voltage goes all the way from plus V peak to minus V peak, here to here. So in 2 cables lying next to one another and connected to different phases of the AC supply, the difference between one cable and the next can be twice V peak. Now, when we use our AC line socket to power something like an electric kettle, we're not really interested in V peak. We're interested in the average power that we can get from the device. Now, the average of this waveform is 0, right? Because there's as much positive as negative. But we know we don't get 0 power out of the plug on the wall. Well, let's go back to our definition of power, current times voltage, P equals IV. If we rewrite I as V over R, we see that the power is V squared over R. So if we want the average power from our wall socket, we want to average the quantity V squared and divide it by R. Now we see that V squared is always positive, because when this crosses through 0 and becomes negative, V squared is again positive. And so what we want is a quantity called the root mean square value of this waveform, and that turns out to be 120 volts for your wall socket, about 0.7 of the peak value, And so the peak value is close to 200 volts. So for two cables lying close together, the largest difference could be about 400 volts. And that's why you'll see printed on the insulation of cables that connect power, typically 600 volts rating insulation to be safe. Okay, so those are the quantities associated with an AC waveform. And once again, the RMS value of a waveform is given by the peak value divided by square root of 2, or the peak value, if you know the RMS value, 120 volts for your wall socket, is the square root of 2, or about 1.4 times the RMS value gives you the peak value. Now, we mentioned an AC signal of 120 volts RMS value, but the signal coming into your radio could be microvolts, and that is a huge range of amplitudes to talk about. How do you talk about it conveniently? Well, a convenient way of doing this is to use a logarithmic scale. And so let's illustrate the decibel scale, which is the conventional scale used in electronic circuits. The deci comes from a factor 10, which makes the original logarithmic scale opposed by, I believe, Mr. Bell, more realistic to give you the decibel scale. And it is defined as 10 times the logarithm base 10 of the ratio of two signals. Now, sometimes you'll hear about values expressed in dBs as an absolute value, but it always means relative to some value. So if it's an audio power, it would mean relative to, for example, 100 milliwatts. So let's just go through a calculation here. If we say one signal has a peak value A, another signal has a peak value B, what is the ratio of A to B in decibels? The answer is it's 10 times log base 10 of A divided by B. So let's give you, take a concrete example. Or before we do that, let's get to the power ratio. The power ratio is 10 log base 10 of A squared over B squared, because the power is V squared over R, and we're assuming the same resistor. Now, the log of a quantity squared is equal to twice the log of the quantity, because the exponent can come out and multiply the log. So 10 log 10 of A squared over B squared is the same as 20 log 10 of A over B. So let's put some numbers in. Let's take A being 1 millivolt and B being 10 volts. So we want to find 10 times log base 10 of 0.001 volts divided by 10 volts. That is 0.0001 volts, and then the log of that is -4, 10 to the -4 is what gives you 0.0001, and then you multiply that by 10 to get 40. That's 40 decibels minus 40 decibels. So we would say that signal A is minus 40 decibels with respect to signal B.